Hello everyone. In this video I would like to show you how to use the Bayesian or probabilistic inverse modeling capability of OpenHydroQual to infer the kind of posterior probability distribution of parameters when you have observed data. So I had an earlier video where I showed you how to do deterministic parameter estimation using genetic algorithm. In this video I want to go one step further and show you how to do probabilistic parameter estimation, because we know that there are uncertainties associated with the parameters when we do parameter estimation, and we want to basically estimate those uncertainties essentially. So what I'm going to do is that I will use this simple example that I used in the deterministic parameter estimation case. I will do a deterministic parameter estimation, and then I'll do basically probabilistic parameter estimation after that, so that we can compare the results. So I have this model which I'm gonna share with you. I'm gonna provide the link in the comment section of the video on YouTube. So the model that I have is very simple. It's just a single reactor, and basically I have this pollutant or dissolved species undergoing a first order decay. So if you look, we have one constituent, it's called constituent A, and it undergoes a first order decay, and then we have this reaction parameter called KD, which I've assigned right now a value of 1 to, and then the initial concentration of this pollutant A is 1 grams per cubic meters, or 1 milligrams per liter. So I can first just run the model in forward mode. So in order to do that, I'm going to click on this, the icon for running the model, and then I can look at some model predictions. For example, I can look at the concentration of A in the reactor. As you can see, it undergoes an exponential basically decay, or first order decay, and so that's the forward model. It's a very simple one. Now I have some observed data representing, let's say, the measured concentrations at different times in the reactor, and I want to use that to estimate two parameters. One is the first order decay rate, or KD, and also the initial concentration. So basically, let me first add the observed data. So what I do is that I right click on observations, I add an observation, right? So basically now I have an observation, and for the observation I need to provide some information. So basically, let's first, first of all I'm gonna say, let's first change the name. So it's gonna be, I'm going to call this observed concentration. It's actually observed concentration of A, but A is the only chemical species that I have. So, and then the object is reactor 1, and the expression is going to be A concentration, right? So A colon concentration. That means what we are measuring here, what this data represent, is the concentration of species A. The observed data, I have this time series data, which I'm gonna provide the link to in case you wanted to try this. So I'm gonna basically, on my computer, the observed data is actually saved in this file called observed data for inverse example. It's right here. So I'm going to add that. You can look at it. I can just right click on the file name, then plot, and that shows me the observed values. As you can see, there are some errors. I mean, basically the data is kind of wiggly, because that's how actual observations typically look like. And so anyways, now what I can do is, let's just compare our model predictions with the results. So I'm going to save this the model so far, and now I can run the model again. So I'm going to run the model, and what I can do is that I can see how my model predictions compare with my data without any calibration, of course. So basically if I right click on the observed basically this observed concentration, I can now look at the model prediction by clicking on results and then expression. So this is the model prediction, and then I can also look at observed data. So I can basically compare them. I can copy the observed data and then go here and paste. And as you can see, there's a bias, there are some discrepancies as we expect because the model is not calibrated. I just basically entered the model parameters sort of arbitrary. Now let's do deterministic parameter estimation first, and then we're going to move to stochastic parameter estimation. So in order to do deterministic parameter estimation, we need to introduce some parameters. Okay, so here what I'm going to do, as opposed to this earlier example when we did the deterministic parameter estimation, I'm going to add one additional parameter, and that's our error standard deviation. So it's actually when we do the probabilistic parameter estimation, and both actually in deterministic and probabilistic parameter estimation, the likelihood function is calculated based on an error structure, which in OpenHydroQual can be log normal or normal, but in both cases it also requires an error standard deviation. Now in the case of deterministic parameter estimation, the value of the error standard deviation will not matter, will not affect the value of the parameters, because basically all we are doing is we are basically minimizing the squared error, right? And it's since we only have one observed data, it doesn't matter what the error standard deviation is. In the case of stochastic parameter estimation, the error standard deviation will matter, right? So anyways, I'm going to introduce three parameters therefore, right? So the three parameters are going to be my KD, the decay rate, initial concentration, and then the error standard deviation. So let's do that. So I'm going to add three parameters. So I did this 3 times. Now I have 3 parameters. The first one, I'm going to call this KD, but not so we don't mix this with or the model don't confuse that with the reaction parameter called KD. I'm going to call this KD underscore param, and then I'm going to call the second parameter let's say ini concentration param, and then the third one I'm going to call it error standard deviation, or error underscore STD. Now I'm going to assign some values. First of all, for the KD param, I'm going to assign a value. This value is going to be used when I run the model in forward mode, and then I provide some range, right? The range, the upper limit and lower limit, what the way they work is, when I do deterministic parameter estimation, that's the range of parameter that will be searched, right? In the case of probabilistic parameter estimation, the range is the 95% credible interval. So basically, the OpenHydroQual assumes a prior distribution based on the prior distribution that I will provide, and they will set the parameters of that prior distribution so that the 95% credible interval, 95% confidence interval is determined by the upper and lower limits. So I'm going to say the low. Actually, I have to go with the upper limit first. So the upper limit, let's say, is 2, and the lower limit is, let's say, I don't know, 0.3, something like that. And basically, and then the prior distribution, I could go with the normal. But I think in this case, because my lower and upper limit are almost 1 order of magnitude different, it's better to basically consider a log normal distribution for the parameter. So that's what I do. And then I do the same thing for initial concentration. So let's say the value is 1, and then I'm going to say the upper limit is, let's say, I don't know, 2. The lower limit is, in this case, I have a better idea about what the initial concentration is. So let's go with 0.7. And then in this case, I'm going to keep, let's say, I don't know, I'm going to keep the prior distribution as normal. The error standard deviation, I don't have any idea what it is. I mean, I can look at my observed data and get a sense of what I expect. So for example, I don't know, if I look at the values, the observed data, this is the value. So basically, I don't know, the values range something between, I don't know, 1 and 0 and 1. So I think it's my error standard deviation is not going to be larger than 1. But the minimum value, I pretty much, I can't really say based on this, but let's go with, I don't know, 0.05 for this case. We can always do some trial and error. So what I'm going to do is the value, let's say, I'm going to say 0.1. I can do the prior distribution log normal again. And then I have to make sure that when I set the prior distribution log normal, my limits none of them can be 0 or negative. So basically here I'm going to say the upper limit is 1, the lower limit is 0.05. Okay, so now I have the parameters. Let me save. Then what I want to do is that I want to assign these parameters to the things that I want to assign them. So at this point, the model have no idea how to use these parameters. I have to provide that information. So what I'm going to do is that I will go to reaction parameters. So this is reaction parameter KD, and what I want to say is that as the value of the reaction parameter, use this parameter KD param, right? So instead of 1, use this KD underscore param. So what I do is that I right click on the value, I pick the parameters, and then I choose KD param, right? And so that's one thing. Then for the initial concentration, this is my initial concentration, which is 1 right now. I want to change it and set it to be my ini conc parameter. So I'm going to right click, go to parameters, and then I'm going to pick ini conc parameter. So that's what we have. And then for the error standard deviation, I go to my observed concentration, and if you look, we have this error standard deviation, and now what I want to do is that the error standard deviation, I want it to be taken from my error standard deviation parameter, right? So I'm going to just right click on error standard deviation, go to parameters, and then I choose error standard deviation. Okay, save it. Now our system is ready to do deterministic parameter estimation. Let me check the settings for basically I have to check the settings for optimizer. So what we have is we have a bunch of parameters. Most of them I'm going to keep what they are. So what it does is these are genetic algorithm tweaking parameters. The most important things are the number of generations are going to be 40, and the genetic algorithm population, or the number of individuals, are going to also be 40, which is a good number for the simple problem that we have. It's probably more than enough. So now what I'm going to do is that I will run the basically maximum likelihood inverse modeling or genetic algorithm parameter estimation by clicking on this icon that says inverse run. So I'm going to click on that, and so basically what you see here is the y-axis here is the fitness, the x-axis is the generation. So the fitness actually is the minus log of likelihood function. So basically what we do is that we minimize the negative of the log of likelihood function, which is actually maximizing the likelihood actually. So so as you can see, after generation, I would say 14, we don't see any improvement. So that means with kind of 14 generations, we were able to basically estimate the optimal value of the parameters. So now what I'm going to do is that this is done. I'm going to close it, and then we can look at the deterministic values of the parameters. So if I click on the parameters, you can note that the values are changed to changed from the values that we initially specified. So we got a 0.807 for KD, and then initial concentration is 1.02, and then error standard deviation is 0.56. So as you can see, the value that was estimated for the error standard deviation is kind of pretty close to our lower limit. So it may be a good idea now to change the limits of the error standard deviation. So basically what I'm going to do is that I'll change the lower limit maybe to 0.03, and then I can also change the upper limit to maybe 0.1. Okay, so I'm going to save it. So by the way, we can also look at the match between our modeled and measured results right now based on the estimated parameter value. So if I go to observed concentration, I can look at the modeled results. So this is the modeled results, and then we can also look at the observed data, and I can copy the observed data and then go to paste it on my modeled results, and you can see the match is better. So now we're going to do the stochastic inverse modeling. So let's check first the settings for Markov Chain Monte Carlo. So we can go to settings menu and then pick MCMC, and then we can look at the properties. So I'm going to make some changes here. First of all, the number of one of the important parameters is the number of MCMC samples. So this is the number of samples that will be extracted. I'm going to actually increase this by a factor of 10. So I'll have 10,000 samples. By default, I'm going to have 8 chains. I can also change the number of threads to be used, which is currently 1. That means only a single core will be used to do the Markov Chain Monte Carlo sampling. But I can actually change it to, I mean, this computer has 8 cores, so I'm going to use all the cores. So I'm going to change this to 8 cores. Then I'm going to also, so there's this parameter here called, actually this is it, number of samples to be discarded, burnout, okay, which is currently 0. So that means initially the MCMC will actually start from the parameters that are now set, which is based on the maximum likelihood estimation. But it's always, the initial parameters are always off. So in people who are familiar with the Markov Chain Monte Carlo, they know that we have to discard a number of samples at the beginning because they are not really reliable. So basically what I'm going to do is I'm going to change this number of samples to be discarded to, let's say, 2,000. So I'm going to discard the first 2,000 samples. Then I'm not going to change so desired acceptance rate. What it does is that basically the algorithm starts from a perturbation factor, and then the perturbation factor is adjusted so that we get an acceptance rate of 0.15. So that means 15% of our samples will be accepted, roughly speaking. So I'm going to keep it for I can keep it at 0.15. People who are not familiar with the Markov Chain Monte Carlo, just know that 0.15 is a reasonable value. Then I'm going to also make another change. So basically, after the MCMC is done, the program will sample from the parameters, from the model parameters, and we'll do forward modeling. So essentially, we'll do a Monte Carlo simulation, and then we can estimate the kind of the prediction confidence interval, as you will see. So the larger the number of post-estimate samples are, or post-estimate realizations are, the more accurate those sort of confidence interval of the predictions will be. So what I'm going to do is I'll change this to 400, and then I'm not gonna change. I mean, you can play with other parameters, but I'm not going to go into that. So I'm going to just keep all the other parameters for the MCMC the same. So I'm going to save this, and now we're ready to do the MCMC. So you see these 2 dices. That's the icon for MCMC parameter estimation. So this is it. So I'm going to click on that one, and the simulation will start. This is going to take a little longer. We are actually doing essentially 10,000 simulations. In the GA, in the deterministic parameter estimation, it was 40 times 40 because they had a population of 40 and 40 generations. So that was 1600. Here we have 10,000. In the meantime, let me explain what the graphs that you're seeing. So the top panel shows our acceptance rate, right? So this is the percentage of samples that are being accepted. And the desired value, if you remember, we set it to be 0.15. So anytime the acceptance rate falls below 0.15, the perturbation factor is decreased. And then anytime it goes beyond 0.15, the perturbation factor is increased. So, and basically the second panel shows the perturbation factor. Actually, I think every 400 samples, the perturbation factor is adjusted. That's why you see these steps. Okay, so let's give it a couple more minutes. So we're almost there. This process can take much longer if your model is more complex. The model that we are using is actually very simple. Every simulation takes, I don't know, seconds. If you have a model that is, more complicated, of course, this process will take way more. And you may want to use a more powerful computer so that you can use more, threads. So anyways, this is done, and then we are doing the code is doing creating the realizations. So this is done. Okay, now we're done. Now let's look at some results. So basically now what I can do is that I can go and see what the posterior probability distribution, the parameters that were obtained are. So if I right click on each of the parameters, for example, I'm going to right click on KD parameter. Now I can go to posterior results. I can look at the distribution. So this is the distribution. The red curve is the prior density. So we have the prior density, which is wide, and the posterior density is the sharp one. So this is the probability distribution of decay rate after our basically MCMC simulation. We can also look at the chains. So I can go to posterior result and then click on Markov chain, and you'll see basically essentially the sample. So we have of course 8 chains. That's why you see 8 curves numbered from 0 to 7, and then this is how they varied throughout the simulation. We can do the same thing with initial concentration. So I can look at the distribution of initial concentration and also error standard deviation. So this is our error standard deviation. It's actually the difference between our prior and posterior. In other words, how much the posterior is narrower than the prior. That informs us about how much information were obtained by from the data through the MCMC. So in this case, we actually achieved a lot of information about KD and initial concentration, but probably because of the fact that we actually narrowed down the range of basically standard deviation parameter, we didn't obtain as much information about the error standard deviation. We can also look at the prediction interval. So if I go to if I right click on observed concentration, I can look at 95% bracket of prediction. So if I click on this one, this is what you will see. So this is actually the range of predictions, the 95% range of predictions. I can compare this with my observed data. So if I copy observed data, so this is what we have, and keep in mind that the range that you see is only as a result of the uncertainty in the parameters. So basically the error standard deviation has not been included. I mean, it can be included easily. I'll do it in the future versions, but at this time this is only the brackets that you see is only due to the variation in the parameters. So that's what we have. And then one last thing before we are done. Oh yeah, by the way, we can also look at all the realizations. So we generated 400 realizations. If I click on this one, we can see the actual realization, the 400 realizations. There's not much information can be gained from this curve. So by the way, all the results are also saved in text files in the same place as I'm sorry, I have a lot of files here in this folder, but just to let you know, the realizations are saved in a text file. The 95% bracket is saved in a text file. The posterior distributions can be accessed here. The MCMC samples can be also found in text files. So if you want to plot them using your own graphing program, you can actually load these files, or you can load these files into Excel and see how things went. And that's all I have for today. Subscribe to the channel and leave comments for me. I love to hear your feedback, and look for my future videos. Thank you very much.